the stress. Let us introduce the concept of stress, as we know that the main problem of engineering mechanics of material is the investigation of the internal resistance of body, because you see, like if we apply the load, always body will react by the third law of the this Newton, that the reaction, like action reaction is there. So as you apply any kind of load, whether it's a uniaxial, biaxial or triaxial loads, always a kind of resistance will take place. So whether you see, like these kind of resistances can be well set up within the object or not. So as we can say that the internal resistance of body, or we can say the nature of forces which are being set up within the body, which can balance or not. If it cannot balance, then body will break. But if it can balance, whatever the applied forces are there and internal forces, if they can well set up within those objects, due to the external application, we can say that the body is well established under the application of load, because load is always, you see, as I told you, that force can be like defined by two ways. One by magnitude, that is mass into acceleration, that is nothing but the load, and by the point of application, how these forces are acting on an object, and accordingly the resistance forces are coming, and we are saying that the intensity of the internal resistance is the stress. Okay. The internal resistance is per unit area, that is the intensity. And the external applied load, as I told you, forces are always termed as the loads. Now you see these external applied forces, which are the key generation of the these stresses, can be due to many of the reasons. Like first, the basic reason is due to service conditions. Means you see, like the objects are under the cyclic loading or the tensile loading, or any, like you see, as we are going towards any of the machine, if you are analyzing, we'll find that the bearings are there, the gears are there, the shafts are there, they are always under the different kinds of loads, and accordingly we are considering if we want to design the bearing, if we want to design the shaft, if we want to design the gears, or if we want to design any of the static part of the machine, we are always clearly observe that how these forces are being set up, or due to the environment in which the component works, whether you see it's on the normal temperature condition or severe temperature conditions, and because of these things you see the thermal expansion are there, or we can say later on that it's a thermal stresses are there, or you see through another reasons for the applied forces are through the contact with other members, and that is why you see the contact mechanics are there, and we are here concerning about that how deformations are being taken place due to this interaction. And then you see due to the fluid pressure, that you see if rho z h, if we are saying that rho is the density, z is the the gravitational acceleration, and height, up to how much height these fluid pressures are being exerting on an object, on and in that even the g is there, that is the gravitational acceleration or the inertia forces. Due to inertia forces also you see there is one of the basic reason that the stresses are inducing in an object. So now you see, if you come to the main point, that these internal forces give rise to a concept of the stress. Therefore, we can say that the stress is nothing but the internal forces, or the internal intensity of the forces, like internal force per unit area. And if you see this figure, in this figure, as we have used the rectangular bar in which there is a axial pulling, and since it is a uniaxial pulling, so we can see that this is the P or F, this is the tensile force, which is the extension is there, and if you want to analyze those things, first we need to see that whether this object is under the stable condition or not. If it is under stable condition, that means whatever these forces, the axial pullings are there, they are well set up within those object. That means you see whatever the internal these resistances are there within this internal resistances are there within this object, they are well set up. And these internal resistances are basically due to this external this excitation force, that is P or F, which is there in terms of the Newton, and always we are concerning about these forces because of where the point of application of these forces are, and that's why we are saying that these are the tensile pulling. Like here you see from both ends, this is the tensile pulling. So if you want to analyze those things, first we need to make the cross section, and that's why you see in this diagram we have shown here that there are two main parts, and on both of the side, both of the end sides here, the P external excitation force is there, and due to this externally applied load, we have seen that if you cut those things at both ends through this x-axis line, these internal resistances are there. So each portion of these rectangular bar, either on the left or right side, is equilibrium under the action of these applied load, the tensile load I should say, and the internal forces are always acting at the x action just opposite to the applied load, and that's why you see we can say that this is the well established or equilibrium region. And if you are talking about the analysis of the stress or strain within those things, we can say that the stress is defined by the force intensity or the internal resistance forces per unit area, and hence we use the symbol sigma just to represent the stress, that is P by A, where A is the cross sectional area here, which is the rectangular area is there because the rectangular bar which we have used in the previous case. So here we are using an assumption that the total force or the total load carried by these rectangular bar is uniformly distributed all across the area, because if the load is non-uniform, then definitely you see the deformation or whatever the internal resistances are non-uniform, and then we cannot say that this object is in equilibrium position. But the stress distribution, which we can say that you see if the area is different at different regions, the stress distribution is obviously the different, maybe for from uniform or maybe local regions of high stress regions are there known as the stress concentration. So if there is any abrupt changes there in an object, we can say that the stress concentration is more, and we need to design carefully for those kind of reasons. So if you are talking about the normal stress, then there is no problem because this is uniformly distributed because of the uniform force distribution in an object. If the force carried out by a component is not uniformly distributed, as I discussed during the stress concentration over the cross sectional area, we must consider the small segment or small area delta A, which carries a small load delta P, or we can say of the total load P, and that's why you can define the a small segment of the deformation. For that you see the small this stress is there, that is del F by del A, or we can say at a particular stress generally it holds true only when a point, or we can say for a small region, or we can say the infinitesimal region, the sigma is nothing but the limit of delta A tends to 0 del F by del A. So generally what we are doing here, because if we found that there is abrupt changes are there within the object, or we can say object is not uniformly rectangular or any shape, defined shape, what we are doing here, we are simply categorizing this object into various categories, and then we sum up those things, because you see we define the stresses for a small segment as we have seen in this, you see del F by del A. So we can again sum up those things by summing up of this limit of delta A1, delta A2 and delta A3 so on, and then accordingly we can get the total stress out of the whole object. Now you see if you are going for the unit of the stress, because stress is nothing but the intensity of the internal resistances, the basic units in the SI system is Newton per meter square, or we can say the Pascal. Pascal is renowned scientist which gave the concept of the pressure, and pressure was also you see the force per unit area. So it has the same meaning, it is the internal resistances, or we can say internal resistance of the force, or we can say it is the internal intensity of the forces. That's why we can define those things by Newton per meter square or the Pascal, or if you go for higher side of these things, then it is the kilopascal, that is 1000 Pascal, or gigapascal, that is 100,000 megapascal, that is 100,000 Pascal, or gigapascal, that is the 10 to the power 9 Pascal, or sometimes it is pretty common to use the Newton per millimeter square, that is also equals to megapascal. So while this is a pretty common this unit is there in India, or in particular I should say the Asia or European countries, but US, you see in United States of America, they are using this pound per square inch, that is PSI, that is the FPS unit. Okay. And now you see this was the basic concept of the stresses. Now if you are talking about the types of stresses, there are two basic types of stresses. One is the normal stress and one is the shear stress. Normal stress means, as I told you, when the uniaxial loading is there, because of the uniaxial loading, whatever the internal resistances are there per unit area, that is always comes out from the normal stress component, and that's why you see we are categorizing normal stress component by either pulling or the compression, because they are with the uniaxial part. And second, the basic stress is the shear stress. If they are not the uniaxial, if they have some sort of eccentricity, or these stresses are there for a plane where x and y planes are there, means here or here, you see these stresses are being coming through the forces, we are always saying that it's a shear stress. So normal stress is a axial stress, shear stress